Hi students, today's lecture is about controller tuning. So far what we have discussed is we know what are the various controllers. What are the various controllers? So in that we have studied P, PI, PD, PID. Okay. Next we have fixed the criteria like overshoot should be lesser, rise time should be lesser, peak time should be lesser, and settling time should also be lesser, and the decay ratio should be 1 by 4, and I time performance criteria like ISE, IAE, and ITAE should be lesser. Like this is for suppressing large errors, this is for suppressing small errors, this is for suppressing errors for a long time. Okay, so these are the criterias we have seen in the last session. So we have studied the controllers, we know the criteria, and the all the criteria cannot be applied for a single process, but it depends based on the at least 30% or 40% of these criteria can be applicable. So we know the controllers, and we have the criteria, and we have to choose the controllers. Like already we have studied, proportional controller means choose a liquid level or pressure process. Okay, then PI means it is a, this is, it produces sorry, not offset, overshoot. So in that case, you can use, because you cannot use this for a flow. Flow cannot be used because this is also faster, this is also faster. So in that case, you can use liquid level or pressure, or if you are not okay with proportional control, then you can go for PI. Okay, then PID is for temperature process multi-capacity, because it produces more gain. Because it is a sluggish process, you have to fasten it, and so this is also sluggish. This is also, if it does not have more gain means, then it won't work. Okay, so likewise we have fixed the process. So now we know the controllers, we have fixed the controllers for a particular process, and we know the criteria. Then finally, once we fix the controllers, we have to tune the parameters. So what are the parameters for a proportional controller? Kp is the parameter. For Pi, Kp and Ki or integral time. And for PD, Kp and Kd. And for PID, you have to tune Kp, Ki or Ti, Kd or Td. So Ki, Ti are inversely proportional, Kd and Td are directly proportional. So your Kd value is Td, Td value is Kd, whereas Ki is 1 by Ti, Ti is 1 by Ki. So these are the controller parameters. So how do we tune the controller parameters to achieve this criteria? So we are going to see that tuning of controller, that is controller tuning. There are three methods we are going to see. One is Cohen and Kuhn, and in Ziegler-Nichols we have two methods. So totally three methods. So we'll see one by one. Okay, so first tuning is, yeah, this slide says about why do we need controller tuning, and then the criteria such as one quarter criteria, minimum settling time, minimum largest error, and the performance criteria, which is IAC, IAE. Okay, then we can use semi-empirical rule. Semi-empirical means there is no logic, so we can pick certain values and we can put some numbers so that it will achieve this criteria. Okay, so first method is process reaction curve, PRC, or Cohen and Kuhn, because this is developed by Cohen and Kuhn, or we can say CC method, Cohen and Kuhn, or PRC, process reaction curve. And then this is a open loop technique. That is, so you know that this is a process like process, measurement, controller, final control element. So what you do is break the loop between the controller and the final control element, and introduce one step signal. This A could be anything, 1, 2, 3, or any value, any magnitude. So introduce step signal to the final control element and observe the response. Okay, so that is called as, or this is the test we have to conduct for this process in order to proceed with process reaction curve. So we have to break the loop between the controller and the final control element. Hence, the closed loop is open loop now. So now, once you break the loop in this between them, you have to introduce a step signal of magnitude A, and observe the output. So the from the output, you have to derive certain parameters. So now your transfer function becomes, because you have only GF, GP, GM, because the path is broken between GC and GF. So this is the transfer function. Okay. So this is called as PRC, process reaction curve transfer function. So that process reaction curve is approximated as, because we cannot take completely. So it is approximated as K into e power minus TDS and tau s. So from the curve, we have to determine what is K, what is tau, what is TD. Okay. So K is the output at steady state. Okay. So at what output it settles at. So that is B. And then the input you give, the magnitude is K. If you take the ratio, then that becomes K. Your tau is, you have to calculate first, B you already know, and then you have to find out the slope. Okay, for that you have to fix the point of inflection point and you can get the slope. So if you take the ratio between B and the slope, then you will get this tau value. TD is, this is a dead time. For particular time, the system won't respond. So that time is called as TD. So I will show you these parameters in the picture. Okay, so this is your PRC. Okay, when you break the loop between the controller and the final control element and introduce a step signal of magnitude A, which is A by S in Laplace transform, and observe the output. So this is the output. So can you see this S-shaped sigmoid? So this is called a sigmoidal curve. So you have to draw a point of inflection. So that point touches this line. So this line is called as TD. Okay, because for this we need three parameters, K and tau and then TD. So K equal to, so it settles at B and then the input you know. So K equal to B by A. B can be picked from here. A, you give the disturbance. So you can calculate B by A. And then tau is, formula is B by A. So find the slope. So you can take any point. So you can take any point and take the slope. So this is dy and this is dx. So take dy by x, that is called as slope equal to dy by dx. Or in MATLAB directly you have a code. Well, once you fix the point of inflection code, then that particular point is your slope. Okay, so you can take that code also. So you can find out this, yes, and this is your tau, and then this is your TD. Okay, so because we have seen that two response. One is it is approximated to K into e power minus TDS divided by tau s plus 1. Okay. So this is the approximated response. So this is the actual response. So there is no much difference. That is why we have to use this. So now we'll go to the semi-empirical formula. So this is the formula. So once you know K, tau, TD. Suppose if you want to use PID controller, so this is your KC. So to get KC value, you have to substitute K value, and then you have, so this is your TD dead time, and then you have to substitute T value. So you will get one KC value. Okay. Similarly, tau y. So once you get tau y, in MATLAB, you have to use only gain. So you have to take the inverse of it in the MATLAB exercise. And then this is, okay. So this is semi-empirical formula. These this table can be used only if you know the values. So when do you know the values? When you break a loop between the controller and the final control element and observe the response. From the response, you have to calculate B by A is your K, and then this one is B by slope, and this is the elapsed time. Okay. So I did this problem in the MATLAB. Okay. So this is the transfer function, process transfer function. Then sensor, it can be here or here, both are same. Sensor transfer function is 1. This is final control element transfer function is 1. So here I have used PID controller. So in order to conduct this test, first I need to break a loop. So I have broken the loop. I have introduced one step input and then the response. Okay. So here this is the exact response. And then from this, I have found TD equal to zero point 0.5. This point is 0.5. The slope is, so here the slope is 0.13 by drawing a point of inflection line. This is 0.13. Okay, then 1 by S. So slope 1 by 0.13 is tau. So now I know tau value, TD value, and K value. So first you have to get the graph, and then this is the exact response. And then you have to find out the point of inflection. So point of inflection occurs at 2 point. Okay. So from this you have to find out the slope. So from this point of inflection you have to draw this slope. Okay, take these 2 points and get the slope. So we know all the values, then straight away we can substitute in the formula. So this is your transport delay, which we form it as 0.5, and this is the transfer, this one transfer function. So here using this, we can check. This is the exact response. So this is the exact response. This is the approximate. We can check only small difference. So this is to check. Okay. Then our controller is PID controller. So we have to calculate KC value, tau value, and tau D value, and then use here. This is in MATLAB. In MATLAB, you have KP and the KI. So convert this to this, then KD equal to TD1. So substitute and get the response. So that response is like this. So this is the control. See, our input is 1. So it settles properly. Okay. So this is how we are to tune. So once again, we'll revise. What's the first thing you need to do? You have to conduct the open loop test. How to do that? Open loop test. Break break the loop, break the control loop between controller and the final control element. So then once you break, then you have to introduce step signal that should be given to the GF office controller block, this final control element block. Then second point is observe the response. So that response is like this, S-shaped curve. So from this, you have to get the transfer function as k into e power minus TDS divided by tau s plus 1, where k is b by a, and then tau equal to b by slope, and then TD equal to elapsed time. So compute everything and put it in the formula and run the, then again connect the, how do you check? Then connect closed loop fashion and check the response. Definitely a response is settled. Okay, so this is how you have to do. You can practice the same in MATLAB. Okay, but the problem is you should have a S-shaped curve. So always open loop system produces S-shaped curve only. So the next one is Ziegler-Nichols. So in here we have two type of test. One is open loop test, another one is closed loop test. So the Ziegler-Nichols method is optimized for 25% offset. That is, this is 25 percentage. Okay, it's 25 percentage in the sense, suppose if this is 1, then 0.25. So this can be added as 0.25. So 0.25. So both the tests are aimed for 25 percentage maximum overshoot. Okay. So in the first method, just take a plant. It's an open loop test. Just take a plant, give one input signal and observe the response. This should be S-shaped. If this is not S-shaped, then we cannot use this method. So that is the first condition. A curve should be, the output should be S-shaped curve. Okay. So if in your system, if you have 1 by S or if you have e power TD, definitely it will produce S-shaped, or it may not produce S-shaped. So you have to take care of that. So this system should produce S-shaped curve. Okay. So once you get the S-shaped, so you have to get the parameters. So here the parameters are this elapsed time is L. In that we have, in PRC we use TD. Okay. And then this is your time, tau. But in PRC we use B by S, but this is the capital T. Okay. So this is the K value. So K value, T value, and L value. L value is the elapsed time. Then once you draw the tangent to the curve, then it touches the input at one particular point. So this elapses time to the this particular point is capital T, and then this gain is K. Okay. So once you know the values, directly substitute here. Okay. So based on this, we can get the controller values. Once you get the controller values, then substitute in the controller block and observe the response. This is the first method. Okay. Then in the second method is a closed loop method. So what we do is, so first you should have all the blocks, plant, and then here a sensor, and then here final, you can have all the block, but use only proportional controller. Don't use any other controller, use only proportional controller and introduce some input. And what you do is first try with one or two, some gain value to this and observe the response. For example, for this particular K value, let's say 8. So what you do is take the plant transfer function. Then if you have sensor transfer function, include that. If you have final control element transfer function, include that. But you have to use only one controller, that is proportional controller. Let's say it is 8. Okay. And observe the response. If the response is So this is the input. If the response is like this, for what? Kp equal to 8. Okay. What you do is, so it is overdamped. So which means you have to decrease this. So in the next case, you have to decrease. So take some 4 value. So if you give 4 and then your response is like this. So if your response is, so this is over damping, this is under damping. Okay. So if your Kp is 8 and if your Kp is 4, so for example, sorry, let's take this as 4 and then this as 8. Sorry about this. Okay. So whenever you take Kp equal to 8, suppose if your response is like this, which means it is moving towards unstable condition. So you have to decrease the value and check, but it is stable, but it is not sustained. So your controller range is between 4 and 8. So you have to keep on changing the value between 4 and 8 until you get sustained oscillation. Sustained oscillation means the magnitude should be same. So until you get sustained oscillation, you have to keep on tuning this variable. So this is called as Ziegler-Nichols test. So how do we do that? We have to conduct a closed loop test. For that, choose only proportional controller. First, you randomly choose one Kp value and observe the response. That response belongs to either this case or this case. If it belongs to this unstable condition, then you have to decrease the Kp value. If it is belonging to the stable condition, you have to increase the value. So your curve is like this. So like this, and then it moves. Okay. So your controller value lies between this. So if you use this value, then it produces sustained oscillation. So you have to check that sustained oscillation. Once you get that sustained oscillation, you have to choose for which gain value you will your sustained oscillation is guaranteed. So that is called as your ultimate gain. Okay, Ku, because your equation in this is based on Ku and Pu, ultimate gain and ultimate period. So how do I get that ultimate period? So I have to take the sustained oscillation peak to peak duration. So this duration is Pu. So this is Pu. Okay. So once you do that, so once again I'll repeat, in Ziegler-Nichols closed loop test, we have to conduct test closed loop test to derive these values Ku and Pu. So how do I do that? First, start with simple proportional controller and keep on increasing or decreasing until you get sustained oscillation. And then for which value you get sustained oscillation, that is called as Ku. And then the time between these two peaks is called as Pu. Then substitute directly to get the values. Okay. So we'll check this problem. Okay, so in this problem, you have integrator. So the first method should have S-shaped cave, but because of the integrator, the S-shaped cave won't occur. So we cannot use the first method. So let me try the next method. So in the next method, I need to check for what sustained oscillation, because first method is S-shaped curve, second method is sustained oscillations. We all know this. In control system. We have studied Routh array. So Routh array, for example, this is S plane. Okay. So here the curve starts like this and it settles. And then this side, if it is S plane, left hand side produces like this, right hand side produces like this. But on the imaginary plane, it produces sustained oscillation. So we have to check for which value the response stays at the imaginary. So we have to find out the sustained oscillations using Routh array. Okay. So in this, we don't have chances for negative value. So all values are positive. So sustained oscillations is impossible. So we cannot apply both first method and second method. So like that, you have to check before you do this. S-shaped curve for Ziegler first method and then sustained oscillations for the Ziegler second method. So okay, previously we have analyzed both the methods are not applicable because of the integrator, it will not produce a shaped curve. And when we tried with Routh-Hurwitz criteria, then there is no chance for the system to produce sustained oscillations. So we are dropping these two methods for that particular transfer function. Okay, then we are moving into this another case. So Ziegler-Nichols, we have already discussed. The maximum overshoot is approximately 25%. So we are going to check that. Okay. So for that, we have taken one system, 1 by s into s plus 1, s plus 5, and then we have PID controller. So let's check. So this is the process. So we have given one step signal. This is the response, just a response. So you have a S-shaped curve. So you can use a Ziegler-Nichols first method. And then we'll check whether the sustained oscillations are happening with this method. For that, you have to use, you have to take the characteristic equation. Characteristic equation means you have to take the closed loop transfer function. So then take the characteristic equation, then put S and 5, I mean 1 and 5 here, and then 6 and kp here, and then apply the formula. Then at what cases this term will be 0 to produce sustained oscillation? If kp is 30. So now we found that kp is the value for which the sustained oscillation is happening. So for that, kp is 30. Okay. So once you get that value, so you have to substitute. So we have to take the transfer function s cube plus 6x square plus 5 is the transfer function. In this place, you have to replace, because I need to find the omega value. So s can be replaced by j omega. So replace that. Then you have to collect the real parts and the imaginary parts. And then your from this, the imaginary part is for sustained oscillation. So from this, omega equal to square root of 5. So how to get the ultimate period? 2 pi by omega. So omega substitute the value and find this ultimate period. So now your we have found that Ku equal to 30 and Pu equal to 2.8. So substitute and get the control parameters and you implement automatically the process will be controlled. So this is how. See, it's a transfer function. This we have used Ziegler-Nichols for aiming for 25% offset. So we can check that. So here this is the input. So 1, 2, so it is more than this. So it is more. So it is not maintaining 25% offset. So we have to reduce the value. We have to tune the parameters and go for it. Okay. So this is how we have to do in MATLAB. Okay. So how to do the test? Just to recap. So first connect this transfer function. Put the transfer function. Then you have to use proportional controller KP. Then connect this. Then connect this. So here you have a error detector. That's it. Okay. First start with different values. Start from 1 to 50. And for each and every value, check are you getting sustained oscillations. But from the theoretical calculation, we found that when it is 30, sustained oscillations is there. So you have to calculate this PU. Okay. But theoretically means you have to substitute S equal to j omega and find out omega. Then ultimate period is 2 pi by omega. Okay. So this is theoretically, this is in MATLAB. So MATLAB is so easier. Just you have to connect the controller, just one gain value, connect the process, keep on changing the value till you get sustained oscillations. Once it is done, note down this value and note down the peak, successive peaks. Find the value and substitute in the equation and you will get the controller parameters. Then implement the controller parameters. Now it was in proportional control, then move to PID controller, substitute the parameters and make sure from this table you will get only integral gain. But in MATLAB, it will take only not it will not take integral time, but it will take only integral gain. So you have to take the reciprocal of this is equal to ki. Okay, you have to do this exercise. Don't forget to do that. Okay. So now we'll do this process with using Bode plot method. Okay. Yes. So this is the function. So here we can write the equation. Okay, so we know that. How do we write the equation? Because we always, whenever we want to find out the gain margin, we have to equate that to minus 180 degree. So minus 180 degree equal to tan inverse of minus omega c. I mean, this is the cutoff frequency. Okay. Similarly, minus tan inverse of 10 omega CO and minus tan inverse of 2 omega CO. Then keep on changing the value until you get minus 180 degree. Then it is proved that 0.415 you will get the 180 degree. And then this is for ultimate period. Then you have to find out the magnitude value. So log AR, this is the amplitude ratio, log of 1 by, you know, the square. I mean, this is real part square plus imaginary part square. So here also real part square, imaginary part, take a log, and then from this you will get the answer as 0.08. So omega you have to substitute 0.415. So you know all the values. Substitute 0.415. So now you will get 1.08, and then Ku is equivalent to 1 by logarithm of amplitude ratio, which is 12.6. So now we know the ultimate gain, and we don't know the this ultimate period. So use the formula 2 pi by omega. So 2 pi by 0.415. So you will get this PUs and substitute in this. So if it is a proportional controller, these are the values. PI controller, these are the values. And the PID controller means these are the values. But how to do that? For that, we have a formula. So for this, for proportional controller, what is the formula? KU by 2.2. So this is for proportional controller. And for PI controller, it is KU equal to, sorry, KU by 2.2 is KP, and integral time is PU by 1.2. Remember, this is integral time only, but in the MATLAB, you have to convert to a gain, you have to take the inverse. And for PID, it is easier to remember. So ultimate gain by 1.7 is your KP, and PU by 2 is your integral time, and PU by 8 is your derivative time. So now we know all the values, and straight away implement these values in the controller block, and you can run the response. Definitely your response will be a controlled response. Okay, so this is how you have to tune. So just we'll see the recap on that. In this unit we have studied various controllers characteristics also we have studied. Then next one is we have fixed the criteria such as overshoot, rise time, and time integral performance error like IAC, IAE, ITAE. We have studied all those, and we have fixed the criteria, and we have chosen the system like proportional controller is for liquid level process or gas process. Even PI control is for that process, and PID it is temperature process or multi-capacity. So once we do that, and once we fix a criteria, we can choose the controller. Once the controller is chosen, then we have to tune the parameters. Okay, so to tune the parameters, we have three different methods. One is PRC, that is process reaction curve method, which is devised by Cohen and Kuhn. So it is fully semi-empirical formulas. So for this, the condition is it should be open. The test should be conducted on open loop basis. Get the parameters like capital A, tau, and TD. Substitute this and get the controller parameters, and substitute in the PID controller block and check the response. The another method is Ziegler-Nichols. In Ziegler-Nichols, we have two methods. One is open loop and closed loop. Open loop is you should have a shaped curve. Closed loop is you should have sustained oscillations. So the sustained oscillations can be found using this Bode plot method, or it can be directly applicable to the route array and get the values. So once we get Ku and Pu, for this the parameters of Ku and Pu, for this the parameters are L, capital T, and capital K. These are the parameters. Once we get all the parameters, then substitute the formula and get the controller parameters, and it should be directly substituted to the controller block, and you can check the response. Definitely your process will be controlled. So if any process is given to you, or if someone is approaching you to design or to tune the controller, means you can compare or you can apply all these tests. Okay, many researchers have also been done, but still now they are still using the same tuning method. But there are some empirical rules also to tune the final adjustment. So this is how what our syllabus is. So in the next class, we'll see the system identification. Okay, thanks for watching.